Okay, so now we're getting started. Today's lecture is an important one. And why is it important? Well, for precisely the same reason that the concept of energy is important in engineering. And for some people, this is the central concept of all. And all this talk about signals and stuff is secondary. All right? So, like the signals we've done before, even energy, and this particular mechanical energy, has an economic analog. And this is what we will be calling economic rent. So economic rent, it sounds a little bit funny because you think it's a rent, like you pay a rent for a room or something. But it has historical reasons why it's called like that. And maybe it comes really from Adam Smith and Ricardo, and they saw economic rent as a sort of surplus. So the history of economic rent was that everybody had to work in the old days, except a few people who owned land. That was the only capital that was available, and they didn't have to do anything. Okay, well, that was not totally true. Usually they were in the business of fighting. You know, they were lords or knights or this kind of individuals, and they were in the business of fighting each other mostly. All right? Why? To get more land or defense another one who had land from encroaching upon yours. So medieval society, but also a lot of the ancient societies of the Bronze Age, really consist of two types of people: the ones who had land and the ones who didn't have land. All right, and the ones with land, they got there, and the ones without land had to work for their income, so they were usually working on the land, and the ones without land didn't have to work. Now, why didn't they have to work? Right? Well, the reason they didn't have to work is they had the land, so everybody else can work for them, and they have to give a little piece of the produce of what they received in order to be able to work with the land. Now, why would you do such a silly thing? Well, if you don't do that, then you're not eating at all, right? And you're not working. So this was the only solution available. And then the question came, well, okay, they made a lot of money with this. Well, they would spend it all, of course, on wars in order to defend each other's land because their land was so valuable. But then the question became like, why does this land have value? All right? Why is it so valuable? You don't have to work to get it. It's a free gift of nature. This is the words they use, right? So nature is there, and it just gives you this land, right? And there it is. But yet, you know, if I wanted to use your land, I would have to pay a hefty fee. And that fee in the old days was called the rent. Now, all this fee was not to compensate me for anything else, except for just owning this land, or having the land, or having the power of this land. I wasn't giving you any goods, I wasn't doing anything at all, anything that I had to produce myself. So the idea came, why, where is this, what is this? What is this thing that somehow is represented by the land? And that thing they called the economic rent, or the surplus. Economic surplus was later called, in a later version, okay? And the idea was that land was valuable for a different reason that other goods were valuable, namely because of the economic rent that it would command. All right? So this was a big breakthrough. It was done by a guy called Ricardo. So Ricardo, his parents came from Holland, actually, and they originally came from Spain and Portugal with the expulsion of the Jews. They would move to the Netherlands, and then when Ricardo was very small, before he was born, they moved to England, and he became an English economist. And he was quite a brilliant individual, and he sorted this business out for the first time. And then Adam Smith took it, and then the name economic rent stuck. Now, it's still being used because, if you all will remember, we had a presentation by Shell, and the lady was talking about the economic rent that would come out of their operations. So, although a little bit counterintuitive, I think, the word rent, it's still being used by Shell and everything. So there's really no reason for us not to use it. Okay? Now, what I want to do in this lecture is show you how that is the analog to the mechanical energy, all right? But first, let me give you the feeling behind it, you know? So economic rent is just the stuff that you get for free, that is out there, that you can just use it any way you want. You can spend it on war, but you can also spend it on big parties. They did that too, all right, these guys. They would have big castles and they throw big parties, or you could spend it on gold or anything else that wasn't productive, all right, or productive. So you can spend it in any way you want. So it's a type of money and income that you are completely free to spend however you please. Now, in this sense, it's analogous to mechanical energy. What is mechanical energy? Well, it's either kinetic energy or potential energy, right? But what you can do with mechanical energy, you can turn it into anything you like. You can make electrical energy out of it. That's called a generator or a dynamo, right? You can make magnetic energy out of it, but that's the same generator. You can even make heat out of it. You don't know, by just rubbing the table, you're changing mechanical energy to heat, right? The problem is, if you make heat out of it, you can't go back, right? You can't take all that heat out of if you take a bucket of water, you sit there and you stir a big paddle wheel, you put the kinetic energy will disappear, but will go into heat. But then how do you get the heat out into mechanical energy back again? If you turn it into electrical energy with the generator, you can then get the electricity out of there, run a motor, and then and the thing will just, if you have no losses, you will get it back. All right? So mechanical energy, like electrical energy, is what we sometimes call exergy or available energy. It's energy we can spend whatever way we want. And in the same way, intuitively, that's what economic rent is. It's just something you can spend in any way you want. All right? But not necessarily always get it back. All right, so with that in mind, let's start this lecture and start figuring out what all the things are that go along with this. Kinetic energy, potential energy, power. All right?
A few weeks ago, when we were talking about kinetic energy, you called the economic rent. You said that.
Very good, thank you. Right, so I changed my mind. Right? Thanks to a remark by you or the others, right? Yeah. And I don't even think I changed my mind. I just put that down and it was a mistake. All right? I'd rather say that.
Okay.
Yeah, very good.
So now I'm a bit confused. So
I know, so this lecture, okay. Just pay attention to this lecture, and then after the lecture, I want to hear from you whether you're still confused, right? So this is the good time to be confused, is before the lecture. If you're still confused after the lecture, then we have a valid question. All right, well, thanks. All right, so I'm going to start again from, what I'm going to do is kind of treat this business the way they would treat it in a bachelor course, okay, here at this university. That's not necessarily the right way to do it, I feel, right? So in the more advanced courses in physics, they probably will start with kinetic energy and from that derive what work is. But that's just not the way we do it. We kind of assume we know what work is, and then we work ourselves back to kinetic energy and say, hey, well, doesn't that work out great? But I want to follow that here, all right? And then later we can say, well, what we would have done had everything be fine, right? So you start off with this idea of work. Right? Now, you all know what work is. The way you would do it in a bachelor's course, you will take some force here, and you keep it constant, okay? So I'm just going to assume that this thing doesn't change, right? And then I would take some object. I don't even care what this is, right? If this is a mass, no mass, let's assume it's a mass. And and I'm going to displace it over some distance while I'm exerting this force, right? And that product, I don't know why this is X, right? So I use the word displacement here, and that product is what we define to be the work done on this mass, all right? That should be clear to you. This is how we start. Then later on, we throw everything around and change the force and this, okay? Now let's first put this in the economic context, right? the fixed idea. So what we'll do is we'll take, for this force, we'll take some fee that you got to pay. And it's just a constant fee. It's not changing with anything, right? So you pay a fee to do some, we had, a few lectures ago, we had something called a handling fee, right? So there's a handler, some guy who's got to do stuff for you, and you got to pay him money, say in dollars, right? And you pay him to handle per unit of good, like Adam Smith did this, and he talked about pins, these little pins. So you got to pay him to handle per pin per day a certain fee, all right? And this is the handling fee. So you see that that's the dimensions of a economic force, right? And if you pay him, then it's got to be a credit, right? Credit income. Yes. All right? Then the next step is the displacement. So what's this displacement? Well, you're in this space, and whatever velocity you take, I don't really care, but you're able to say this is a seller, sell so many goods. I don't even care what the time interval is. You just sold so many goods. I don't care where they went to. There are no springs. There's nothing. This is just empty space, and you push through a certain number of goods, okay? That is this S. So that's the number of goods sold. Now, this is just the number of pins, all right? And I multiply the two, and I get the work done, okay? Now, how is this measured? Well, a little easy. If you multiply this by this, then the units will go away. And what you get is something that is like a flow of money, right? It's measured in currency per day, right? So this is where you have to like first stand still and go like, okay, what did I get? If I do some work on you, and suppose then you're going to have some kind of income or cash flow, whatever you want to call it, right? I'm going to call this the benefits you're going to receive, and it's measured in so many dollars per day, all right? Now, if you think of benefits, especially in the English language, this is how we think of benefits. So in the English language, you would have a job, and it will give you a salary, but also give you benefits. And then the taxman will like assess the value of these benefits, okay? So in Holland, you have that as well. We have this auto van de zaak, you get some car, right? And this car represents benefits, but it will represent some benefits as so many euros a day or a week or however they calculate, right? So when we think of benefits, we don't think of, boink, here it is. No, we think of something that flows in time, all right? Okay, we'll later talk about the benefits of ownership, but again, you own something and you accrue these benefits, okay? They come over time, all right? And we monetize them because that's what we're doing. So you see that what happens is the monetary value of everything you receive just increases by this amount. Maybe it was this, and then you get some extra benefits. Maybe you can get some vacation days or something. You capitalize it and you just get so much. Or you get a car to use, or maybe some internet connection at home that you can use for your job or whatever, right? Okay? So if somebody does work on you, right, in this case it's this handler, then that increases your benefits at this rate, okay? So just get that in your mind, all right? So energy, it feels like it's something that is stored, that you put a container, you put all this energy in. Then you think to yourself, so energy must be measured in currency, right? No, right? Always resist that. No. What you get is this flow, right? Okay? Later on, we'll see when we do Hamiltonian mechanics how to turn this into a real dollar value. But you just get a flow of value, right, per day. And so the example is very simple. So many euros per pin per day, but I push through so many pins, therefore I'm paying so much per day. may. Just keep that in mind, okay? And this is very important. So here's the picture, and you can now just all see how this works. So in a sense, this notion of work in mechanics is also the notion of work, because Adam Smith looked at these pin manufacturers and they're doing work. He never really quantified it this way. He got close though, but not in this way, as in work, So it's close. Huh? This is what you would call work also, economically. All right? So now we know what work is, right? So let's go, I'll take this a step further. Any questions up to now?
No.
Good. Now I want to talk about the change in this work. And this is what's called power. So this business of work, of course, was defined earlier, but then another guy came around, and his name was James Watt, and he was not interested in the total amount of work done, but how much better, more work he could do with his machine than you would get out of doing it just by horses running these mills, all right? And he came up with this concept of power, which is the change in the amount of work, okay? Now, you can already see that if you see as power as a change in the amount of work, then the units are going to be currency per day, okay? So you change this benefit stream, right? And that change occurs over time. So that's where that square day comes from. Usually that's confusing, but it shouldn't be. Because just think of it as this benefit stream, and the change of that per day is precisely what you would say. You can also look at the change per year, and then you would just put a year here, and then it will be almost, oh, I did it per year. Yeah, whatever. Huh? I was saying per year? No, I did day. Day, sorry. Yeah. Yeah. This is not dy, that is day. Okay? So this is very confusing, but it's also confusing in mechanics, because when you read engineers, they'll talk about what does it distribute? Does the energy distribute, or does the power distribute? What does it flows? Is it the energy that flows or the power flows? They mix it up, right? So usually they mean the flow of the energy, and that is equal to the power, right? But they might just use the other terms, and so it is in economics, okay? So I don't really like this word power. It was more of an advertising gimmick by James Watt, but it stuck. All right? In Dutch we use the word vermogen. Right? Now, the vermogen, if you look at the balance sheet, the vermogen is measured just in euros. So it goes the other way. It's the integral of the benefits. All right? So just keep that in mind. All right? Now, we can actually just look at this and work our way through what's happening. So, okay, so I'm making these sales. There's the total sales amount was S. So at any moment, my sales are exactly the derivative of this thing, right? So this is just the change of S per unit of time. Okay, if I look at that. Right? That's what we would call the velocity of mechanics, but that's the sales. So many units per day that I'm pushing out. Now, then I can have this this force here, that becomes a desire or a want. Now, when I have a desire or a want, nothing needs to be done with this. I can just have it, and I'll never be what we will say fulfilled. Okay? Just like you can have, I have an outlet here, there's a voltage on it, and the voltage is the analog of a force, but if nobody plugs something in it, then this voltage is never going to do anything useful, right? You may have a force, but if it's not acting on something and actually moving it, nothing is going to happen to that force, right? And so it is with wants. If you have a want, but it's not being satisfied or fulfilled, right? And whatever. Now, this process of making sales, what is that? It's sometimes called fulfillment in companies. So you fulfill a requirement. Okay, so it's almost like you get this process of filling. So they want so many goods, all right? So you fulfill the order, all right? So this fulfillment, that's precisely this velocity. But what are you fulfilling? Well, in this case, you're fulfilling the want, and we do that by multiplying the want with the rate of fulfillment, okay? So there's a physical rate of fulfillment multiplied by the want gives you the monetary rate of fulfillment, okay? But what is fulfillment? Fulfillment is maximizing, increasing your benefits, okay? Benefits are measured in dollars per day. So increasing that, that's fulfilling yourself, is getting more benefits. So a change in the benefit has got to be measured like this, all right? Okay? So keep that straight. The terminology is very suggestive, it's very nice, you know. There's no way that you can say, well, I don't want to fulfill my wants. You know, of course you do, right? And of course you can have all kinds of wants that never go fulfilled, and you can have all kinds of filling that never had a want to begin with, so nobody's ever going to notice. It's like a tree in the forest that falls and makes no sound, whatever, right? Okay? So the velocity itself, the cells itself, does nothing, because nobody may care about your stuff, so you're just disposing it into the trash can, right? Or maybe he gets so tired of you that he will charge you to do so, right? But it just disappears. And on the other hand, you can have a want that never goes fulfilled, and it's just
But
irrelevant.
doesn't the word sale imply that somebody wants it because else you're not?
It does, yeah. So
So
when it's
sales
selling,
sale is not a good word.
yeah, it's more like output. Huh? Exactly. That's right.
Well, just output without sales is not fulfilling anything, right? You're just, as a factory, you can output a lot of stuff and then just store it somewhere.
Yeah.
It doesn't.
Yeah, but that's what he wanted to show.
Yeah, exactly.
Yeah.
Yeah, that's it. That's it. So maybe that would have been a better name, yes. Huh? I had in my mind this little mass, this I element, so then I call it sales. But it could just be a regular point that's moving, you know? And then what happened? I mean, who cares? But so he's right.
Supply.
Yeah, you can call it supply.
Yeah.
But that confuses you with supply and demand, where you would assume it's the supply phenomenon, you know? So maybe output or input is better, right? You know? But you can even have a household that you just have some trash and you put it outside, you know? Like somebody who wants it may pick it up from the sidewalk, but I doubt whether anybody wants your rotten pulp or something, right? So then it's just, who cares? It's never been sold, never been bought, right? Nobody cares.
Yeah, where I live, there's a guy going every week.
The trash.
That's right.
Yeah, now we have that too.
Then he makes money from it.
Yeah, but you have to pay him. I guess that's not a good example. I think you breathe air, you want the air, and then you push out whatever it is, CO2. They want to tax you on this. Huh? But for now, you don't have to worry about how much air you're putting out. Huh? Right? Huh? Okay. So yes, I think this is a good remark. Maybe output or input would have been a better word. Or just
Flow.
yeah, disposition, acquisition, or disposing of. Huh? Sometimes I use that. Huh? And this has the wrong connotation. It's correct, but it has kind of the wrong connotation. So I like your remark here. You see, this business, you're always groping for the right words to get right, exactly the right meaning here. All right, so I kind of like these remarks because it tells me you guys are thinking and understanding. Huh? Somebody is not with the. Huh? All right. So the business of power, what I see is this thing of fulfillment, and I can literally see in this product, you know, this fulfillment. In fact, a product, you know, a product is something funny, and we think that a product is something primitive, but really a product is a function, you know. So normally with a product, you can think of this one acting on that, and this function does that. All right, well, this is a constant. Okay? So you can also think of it in this way. So it's the filling that acts on the want. So this is fulfilling your wants, and this will be the wanting of the fulfillment, you know? But they are symmetrical because you can flip them around, so they're the same. So you can say, I want fulfillment, or I fulfill a want, depending what the active. And there's some mathematics behind this between covariant and contravariant tensors and how they are linear operators. And, you know, a product is a linear operator, right? If you do A times X, this is the linear operator. Huh? This is just a product. Okay? So there's some mathematics behind it where you can make it, you know, very solid that this is really what's going on. And you can change the causality a bit, and we'll get to this when we do want right. So you can either want fulfillment or fulfill a want. It's just a question of changing causality between what is first the want, and then comes the fulfillment, or is first the fulfillment and then the want comes. It doesn't matter. We'll see there are different elements do different things. Okay? But what I want you to see here, and which you obviously see, is just that something that looks a little bit like, it all seems confusing. What is power? It really is quite elementary. But just keep in mind that benefits is a flow, right? And that you're changing this flow, and that's why you get these funny units. All right? And keep in mind that this business of looking at this product is just the business of fulfillment. Okay? Now, how are we now going to calculate the total work? Well, that's clear. We, we define the power to be, in this case, but the force is constant, because otherwise this doesn't work, right? Because then you will have to add. Okay? So that's why we set it up like this. Okay? Well, there's other cases where this will work. And then in many cases when it don't work, and then we don't use it, right? So how do we get back to the work, right? The total benefits. Well, it's clear from this definition that what we want to do is just integrate this, right? Now, I did that here, right? So the total work is just the integral of the force times the velocity, or the total benefits received is the want, the fulfillment of this want. Now, how are you going to do this integration? The idea is that the integration goes from some starting time here to some ending time over there, right? So the only way to do this integration is if we know what the force and the velocity as a function of time. That's obvious. So I'm fulfilling my wants at every moment in time. So to get the total fulfillment, as it were, which is the benefits, I got to integrate over time. Now, you can imagine this is a nasty business, and it is, because this could be any silly function of time, and this could be any other silly function of time, and then you've got to carry out the integration. So that's no fun. So it's a nice little setup, and everybody agrees, but this is not a theory, you see? Only a mathematician will be happy with this definition. As an engineer, you should go like, well, okay, and then how do I make a model? All right? So we got to look for special situations so that we can carry out this integration. All right? Now, one special situation is if ft is a constant, and then this would be a constant times the integral, right? And then that is equal to this displacement f, and that's f times s, and we're just back to where we started. So that is not going to do very much, all right? Okay? Well, this is where we started off. F times s was the amount of work under a constant force. So we got to look for other things. And the rest of this lecture is all about three other things. There are special cases, an R element, an I element, and a C element, under which we can carry out this integration, all right, in an effective way, right? It corresponds to three special cases, and you can clearly see at the end there are no more, all right, of these special ones. You'll have to look more complicated ones. So with those three elements, we'll have exhausted all the special cases, right? So, if you guys are all with me, then I'm going to launch into that, all right? So, let's start with the R element. So this is a damper. We talked about that last week. Good? Now, the damper is a special case. It has a law that tells you that the want is associated with the amount of sales or with the output, say, through this linear function here. In general, it doesn't need to be linear, but in any case, what we know is that the force is a function of the velocity, all right? Okay? And a linear damper, it's a linear function of velocity, okay? Notice the difference. Here, we didn't know anything, but that it was a function of time. Now, we know that it's a function of velocity. So when I calculate this integral, I can plug that thing in, all right? And then I can then I can work this out, and for a linear relation, it will just be this, b times v squared, okay? And then I'll have to integrate that over time. So now I've reduced the problem in another way. All I need to know is what the velocity is as a function of time, all right? And I have not said that the force now is a constant, right? So I have a more complicated situation of a transaction fee. So the simple one was just a constant fee, right? The more complicated one is what is used in these transaction things. That is a percentage of the price. We did that last week. And then you come to a law like this. So this is the typical transaction fee that you will see in the literature, all right? That is linear. Now, of course, you can have very non-linear ones, but then at least there will be some area around which you could do this, all right? Otherwise, you have to do a more complicated integration. You're not integrating some quadratic function of time, all right? Okay? So, again, you're fulfilling a want, and you can, I don't know why I did this, you should really plug this in, and you'll see that. Now you can calculate what the power is just, if you know the velocity, you know the power. All right? So if you know your output, you'll know what the power is. Okay? Normally, this is called the damping law. We call this the transaction fee law. There really is no law. It's just, this is also not really a law, right? It's just what linear damping. There's no law. Right? They call it Ohm's law, but it's not a law. You know, in terms of, it's only a law for an engineer because it applies to resistors that are made to be linear, you know? And the damping law applies to dampers that are made to be linear damping. So it's not really a law of nature. It's more, you should really call this a constitutive relationship that applies to this particular element. It's not at the same footing as F is m times A, where there is a law saying that the mass doesn't change. All right? So it shouldn't be a complete surprise that there is no such thing called a law in economics or finance, although these types are even more liberal, what they call laws, than we seem to be. All right? Okay? And the power, well, you know it's going to be dissipation. Now you're going to say dissipation of what? I want to get to that. Okay? I first want to calculate surplus and conserve benefit. But what are we going to call this fulfillment now? And there's another word that's around, and it's called satisfaction. So fulfilling wants is something that is what Marshall calls the satisfaction. All right? Now, what's the difference, you say, between fulfillment and satisfaction? Now, satisfaction is the maximum, the right amount. That's what they would say in the literature. Fulfillment is just whatever happens, right? And satisfaction is precisely the right amount based on your wants, okay? And that's what we're calculating here. All right, over there, you can have some work integral, and who knows where it came from. You just kind of posit it, and you don't even know whether the work you've done is the maximum or the minimum or the right amount. All right? So the power that's dissipated in a damper, rather than saying it's the amount of fulfillment, I'll just call this the satisfaction, right? But it really is a rate, so it really should be called the satisfaction rate. So how fast are you increasing your benefits? How fast are things getting better for you, right? Huh? There's also the idea behind welfare, okay? It's all consists with growth. How much are things getting better? In this case, it may be taking things out, and the next thing you get it worse for you, all right? Okay? Now, this element we'll be calling a discounter or something. I'll come to that later when we do bond graphs, when we call it that way. Okay? Well, why do I call it that way? Because it's forces. Okay? Remember? From last week, that's what I call it. Just tell me that. Okay, so this is all that work, but I'll think of the satisfaction as the fulfillment done by a damper, all right? Okay? And we'll also work out, because S is also the abbreviation for entropy, and it generates entropy. So at certain points, you just make choices, okay? So the picture simplifies a little bit. Instead of this force, we can now imagine this element called a damper, right? That is charging these transaction fees. We still need to know what this is, but once we know what the output is, or the throughput, or whatever you want to call it, maybe that's the better word, throughput, because that's not sales or, then we know what the wants must be. All right, so once we know how many transactions, we can calculate the transaction fee, and then we can calculate how much that fee will discount our price, if we have a price. Okay? All right? Is that clear? I think so. Then let's keep moving, and we'll do the I element and then take a break. This is going quite well. You get Ozai is not. So now things get a little more hairy. So let's get started here. So now we have the power done by mass, right? Now, this is a busy slide, so we'll just be talking about this slide for a little bit, all right? For a while. So we'll start it off. All right. So first of all, let's just put in our heads again, remind ourselves how the situation looks in mechanics. So you got this mass and it's going, and it's got some kind of kinetic energy, right? That's this thing T, all right? That's the kinetic energy. And then you act on it with a force, and that force does some work on it. So it just, now it sits and pushes your mass, independent of how fast it's moving, right? So you're just moving along, I don't care. Right? Or you gravity, it can work at a distance. All right? That force will change the kinetic energy, right? Yes, if it does work on it. By how much? By exactly the amount of the work. All right? So that change is exactly this derivative here. Now you know that kinetic energy is equal to this. If I take the derivative, the 2 comes down, the p remains, and the p dot appears to get the time derivative. Right? So I just use the chain rule. You guys follow that? If you don't follow that, you will have to go back to your graduate calculus. All right, undergraduate calculus. So what is the result is this. So the power delivered on the mass must be equal to this. Why do I write it like this? Because the kinetic energy depends on the momentum. So if I know the momentum, this is how it changes as a function of the momentum. All right? Now, it is true that P divided by M is V, so I can write this as V times P dot. Okay? Okay? But this is kind of conceptually what's happening. Right? Now, how do we give this all an economic meaning, right? Now, the mass is special because, let me first talk all the way through now, doing the mechanics, and then we'll do the economics, okay? Because this bears some repeating, because you know this, but you don't know that you know it anymore, right? So this thing is okay. So this is just the power, right? So here will be just the power. We don't have a special name for it. This is just the power that is put into the mass, that doesn't, what comes out, right? Now, what is special about a mass? So we have this mass going on, or put this force on, is that we know we can measure the force by looking at the change of momentum. This is exactly what Newton told us, all right? Yeah? So that's Newton's law. This is our law of the domain. Okay, so we got that on the books. And this thing we know too, because we know we can write this. So this is what is called the demand function, how the velocity depends on the momentum, and that's precisely that, right? Because we know P is m times v, right? That's the definition of momentum. So we know a whole bunch of ingredients here, all right? Now what I want to do is just first see how far we can get with that stuff, right? To make a different, to see how that work ends up as kinetic energy, and then we'll go through it again for the economic situation, right? So let's look at the calculation of the work that is done on the mass, okay? So this is just the definition of the work, right? The power. So this will be the power, right? Okay? Now, I know that for a mass, I can substitute for the force the change of momentum. That's the whole point, okay? So, I did that over there, right? Then I know that I can write, two things. I can write the velocity as a function of the momentum, but I also know that this is the case, right? Sure. That's the whole definition of the derivative of momentum, right? Okay? So I can take this combination and just replace it by dp, right? If I do that, I have to change the limit of integration because I'm not integrating over time anymore. I'm now integrating over momentum, right? So P0 is the momentum it had at time 0, whatever it was, and P is the momentum it has at time t. All right? Simple. And if I plug in my definition of momentum, I'll get, what is it? P over m here, and I just do the integration. Well, this is integrating a linear function. You all know that it's a quadratic function and this. Okay? So there's a bunch of steps, and I worked them all out, but really, they're all elementary, right? But what you got to notice here is there's something weird happening, right? All of a sudden, all the time functions are gone. Time has disappeared entirely. It's just subsumed into Newton's law, all right? Since you know what P dot dt is, you get rid of all the dots, all the t's. And all of a sudden, we're integrating from one momentum to another momentum. Time is gone, all right? And this is how it should be, because you just look at what the kinetic energy was at this moment, and then the kinetic energy of this moment. What does it matter how long it took, right? All that mattered was how much went in there, right? With the damper, it mattered how long it took. Sure. And in general, it certainly matters how long it takes. Okay? But here it doesn't. Okay? It's only dependent on the momentum. Okay? So it's as if this thing just has this kinetic energy, what energy is, and just independent of time just maintains it, right? Okay? So this is what we call energy storage, right? So it's invariant under time, as long as you don't mess with it, okay? So you store the energy. It doesn't go in and out when you leave it alone. This is not going to be the case with the damper in general, only with this. Why? Because you just need to look at the momentum that it has. And you know that if you don't mess with it, the momentum is not going to change because that's precisely the force, okay? So now you got what you call an energy storage element, okay? This is a big break, you know? Remember, first we had the force, then the velocity, and the integration. All of them depended on time in some weird way. Now, time's gone entirely. We have a functional relationship. It can't be simpler, and it depends on only one variable. Then this variable we have to know. This is also called, therefore, the state variable. All right? No way of getting around that. Right? But it's not going to depend on how it got there or what's going to happen to it later. It's just a state variable. Okay? Now you see that if we're now going to backtrack and talk about economics, you get the same thing. If this is price, you'll realize that price is a state variable. It's not going to matter how you got at that price, and it's also not going to matter what happens afterwards, right? All that matters is where you are in the what the thing is, okay? If you go to your grocery store, you do a transaction, nobody should care where it came from for that transaction or where it's going to go to. All that matters is that the price is right. And this is the price, and that's it, okay? Don't have to worry about it. If you want to store it and keep it, and you have transaction costs, you have to pay for those over time. You got to worry about the transaction and how fast you can do it and how much you're buying, you know. But those are separate matters, right? Just the pure transaction alone, without any market friction, is ruled by something called price, and it will not depend on anything except the price itself. All right? Okay? Now,
what you said when you were talking about in the mechanical domain, you said it's an energy storing variable, but
yeah.
didn't you mean a momentum storing variable?
No, it stores energy, and it does that as the parameter of how much is momentum. Okay? I say, oh, it stores energy. Say, how much? I'll say, well, so many Newton meters worth, right? Now I know the math, so I'll go like, okay, then that must be, I'll give you this, and then I know what this is.
Okay, so in the same way, so as you say a mass stores energy, then the man then would store surplus.
Yes.
And it does that.
It also stores this in a sense, right? Because we think of price sometimes as a stock variable. Sometimes you don't. You think of it as a level variable if you're an electrical engineer, and it's hard to think of it being stored, okay? But as a mechanical engineer, we think of velocity and position as a level, and we think of momentum as being something stored in something, okay? This object has a lot of momentum, right? Okay? So in this case, it's a little bit confusing because you have this mass and you have a feeling the momentum is in there, and in addition, you know, the energy is in there, right? With a spring or a capacitor should spring and a capacitor is the other way around. So if you use electrical engineering, they would use a capacitor for that. So there's a feeling that the charge is stored in there, so the amount of current, and in addition, the electrical energy that derives from that, okay? And the inductor, they don't think of the magnetic flux linkage as being stored in there, you know? They think of that as a level. The thing is subjective to a certain level of the magnetic field has a sort of intensity that makes this thing go, right? All right? And that's how we think of a spring, is that the level of the extension is at a certain point rather than the charge. All right, so it's a little bit confusing depending on what type of analog you use, and I want to talk about that in the later lectures, okay, these different types of analog. But either way, you kind of think of the energy as being stored, at least in the engineering thing. But in economics, it's a little bit confusing, you know, because is the surplus really stored, right? You know, I mean, I don't see myself as full of surplus. No, I'm entitled to it, okay? So I'm sort of a legal claim on the surplus. But does that mean it's stored in me, you know? You know? Okay, so...
But also, price feels more as a level variable than as something you store. Or am I looking at it wrong?
No, you're looking at it that one way. This is right. But you can also think of something that stores, because don't forget, price is measured in this way. So you can also say it's a storage of value per item, right? And then it's a store of money, of value, okay? You think of price as a level variable, that's more what an electrical engineer would do, huh? All right? But if you take the accountant's view, or finance view, they typically take the mechanical engine attitude. They think of the storage of the money, all right? So they think of their accounts at the bank when it's being credited, that more money flows into it, right? They don't really care what happens to the goods, you know? They'll say, okay, the level of demand for these goods is pretty high. They'll say that is a level, you know? You know, they think of the good market as being levels, you know, the level of demand for housing is really high, you know, okay, huh? You see? So you switch depending on you're focused on the physical goods, and you do some inventory, then you would use more the electrical analog, and if you're more of an accountant and you're focused on the money, you would use the mechanical analog, okay? So mechanical engineers care about momentum, so we think of momentum as being stored, huh? That's how, well, and we do that because that's what Newton thought, you know? So Newton called this the fluxion, yeah? This is the flux, this thing was a fluxion, yeah? And fluxion comes from flow. So he thought of this as the flow of momentum. So momentum he thought of it as something stored in the item. If you read him, that's also their attitude, right? So just to give you back this old idea, they would throw a ball, but they would ask themselves why a force was not required to keep it moving. And the answer was, no, the momentum is stored in there. And it went in there when we pushed it, okay? So the mechanical guys, they think of planets or rockets to have momentum, right? Okay? Does that clear it up? Or at least that makes the confusion clear.
Yes.
Right? So I think it's just a question of perspective, you know? And unfortunately, the bond graphs are built around electrical engineering background, all right? That's not necessarily unfortunately. So that forces us into effort and flow variables. So you think of an effort as a level and a flow of, you know, as being the, you know, the goods, right? Huh? And but they have other bond graphs. There's a very famous paper by somebody called Firestone who says we should really turn it around. All right? Huh? Okay, you can do either way. They're conjugate, you know? What do you call a price? What do you call, huh? You know, you can call credit the price of interest, or the interest rate the price of credit, you know? It doesn't really matter. It just depends on whether you're busy trading the credit or whether you're busy, you know, trading interest rates, you know? Huh? There's different type of traders. All right? I want to talk a little bit more about the slide. I think it behooves us to take a small break now. What do you think?
Yeah.
And then we can all enjoy some cup of freshly ground TU approved coffee, and we'll be back in about 10 minutes, and we will continue the discussion. Let's get going. So we did the mechanical part, that's very clear. Now let's do the economic part. Now, first of all, I want to, we went through all the little steps, how this works, okay, that's great. What I want to do now is take a step back. Now, suppose that you would know, I would tell you that this is a mass or this is a demander en die has een mass of a certain amount of kinetic energy. Emiel, doe even je microphone.
Oh, sorry. Exchange.
Yeah, no problem. Or I would tell you this is a demander and he has a certain amount of surplus. Now, how would you measure that, right? Just think of an experiment. Now, I'm not going to make you do the thinking, but what I might do is I might say, if I'm a mechanical engineer, well, I mean, whatever this is, this kinetic energy, let's see how much work I got to do on it, or I can receive from it, in order to get it to the zero level, right? Okay? So the way I would define it is the maximum amount of energy I can extract from the mass. Okay? That's what I would do. Now, this is how you should look at the surplus. So suppose this thing has some kind of surplus, the function of the price it had. How much is the surplus? Well, I would say, how much can I extract from it? Now, one way of doing it is to put a damper on it and start measuring, just start coming up with all kinds of transaction fees that this poor man is doing. So in order to suck up all his surplus in transaction fees, you can do that. You just, he will still be moving along at a certain point only with at the output of the reference frame, the demand. Right? So he won't have any surplus that he's offering to the market in terms of excess supply. All right? So this thing is extracting satisfaction. We know that. We've done that before. So one way to answer this question of what the surplus would be is that's the maximum satisfaction that I can extract from it. Okay? So another way to say that is that it's the available satisfaction. So it's extra money that is there that you can spend any which way you want. You can just disperse it through this damping device. You can pay this guy, you can pay that guy. Who cares? All right.
So with in my thesis, we should call the surplus. I would then call it the free energy because that is the amount of energy that I can get out of it.
Exactly. All right. Now this is a special type of surplus. It's just anchored on the kinetic energy, right? Now there's all kinds of surpluses. There may be a surplus in a spring. There may be and they may have slightly different names depending on the circumstances. This is what Marshall called later called the surplus. So if you remember in another lecture, there was a demand and supply graph, and it just said right out consumer surplus. Here's the thing, right? So I went, okay, if that's what you call it, right? So you are right. And secondly, they may even do that, but always be careful that you check the terms they use, right? Maybe they say these are benefits, Okay, but I think it's probably that. This gives free energy, but it won't be just the kinetic energy. But you could definitely think of a situation where the Gibbs free energy is in fact the kinetic energy. It's easy, though. It's not what we do because we look at PDV work and all this, but there's no reason. So it's a way of looking at it. So what you want to do here, if you say if you only have work and work gives you fulfillment, and then I have a special type of work where I can kind of easily keep track of it by just looking at the output, the sales, and that is of course determined for a mass because we have a demand function. Then I can use a device like this to measure in a sense what the surplus is, right? Now, if you think of this formula, basically it's doing that, right? It's just looking at what, the satisfaction fulfillment rate is, and it's just trying to figure out, and it's saying, well, I know that this want has to translate into a price difference because I'm discounting, right? And then you just walk your way through it, and then you can just calculate what will end up at the end of this experiment. Okay? So there you are. This is also called the work energy principle. So somebody ended up proving it that this is actually true. It sounds a little bit trivial, but don't forget where we came from. We have two types of force. We have the Newtonian force, and we have Leibniz's idea of a force. This is more like work, right? this implies kinetic energy, right? And that the two concepts were related in this way is what this formula does, okay? So we have this lecture on these differences, and you will see that what this I element does for you, it links Leibniz's idea of a force and Newton's idea of a force. For economics, it links the realization of the want, so the fulfillment of it, right? There's a realized credit, you can also think of it that way, to the want itself, okay? Without its realization. So why do I say, yes?
I'm still a bit confused about what you mean by the available satisfaction, because in the past slide we defined satisfaction as when you have the exactly right amount. So what is the available?
Yeah, so this is the satisfaction, right? You could also say there's a fulfillment. So what I would have here would be BV squared, right?
Yes.
Now, this is the satisfaction, and this is like the total satisfaction over this period, right? That would be in here from t0 to time, right?
Okay.
That is available to take out. How much? Well, exactly this much.
Okay, but then it's still at one specific amount.
I'm not sure I understand that. So, my feeling is you have this, right? Then you want to extract satisfaction from this, right? So you're going to a new one, right? A little time later, right? Okay? So I can look at this difference. Right?
Yes.
Yeah? I can divide it by t, right? So that will be
Yeah.
okay.
Yeah.
And that is equal to that. And that is equal to, if I put if I look at this situation, right? Why is that the case? Because here is a force, this is a, what is it, P dot, here is F, it's exactly the other way around, right? Depends on what the velocity is. So it will pull, the reaction force is like here, right? So I will have that this F, let's just make it equal, is equal to BV is equal to P dot, right? Okay. And then I multiply by V on both sides. And then this thing is equal to that, and this thing is equal to the rate at which you get the satisfaction out of it. I'm still not answering your question.
Yeah.
I'm just repeating what I said, right?
Yeah, but I do get this part, but how you relate available satisfaction, what it is exactly, I don't get that part. Because you just said that the satisfaction is at one specific point, because you're only satisfied one
point in time, right? So at one point in time, this is the power, that's the satisfaction, right? So that's the rate, this is really the rate, okay, at which I'm being satisfied, right? So what this is saying is I can keep satisfying myself at this rate, right, over this period of time, all right? So that's the total amount of satisfaction that will be available to get out of here, and then it's all over. Okay, then I cannot extract any power from it anymore. I cannot extract satisfaction anymore, right? I mean, in this case, why not? Because these velocities are equal, right? And And the damping, when the zero is a zero velocity, it won't generate a want, you know. So this transaction fee guy is not gonna, you're processing zero, I don't charge him anything, right? So you can't satisfy him anymore because you have nothing to offer. You see? Huh?
Okay, I think I get it.
Yeah. So how much energy do you have? Well, you can measure it by looking at how much power you can get out of it, right? So how do you get the power out? You just sit and put some damper on it, and you extract the energy at a particular rate, and that's called the power, right? You have a certain amount of surplus, you can calculate how much it is by seeing if you can get some satisfaction out of that for somebody, right? In this case, this handler guy, this transaction fee guy, right? Now you sit and you do this for a while until you have nothing more to give you. And what happened is the demands are equal, so you're not having nothing more to supply. Right? So he doesn't need to process anything anymore. You're not supplying the market with anything, right? What happened in the mechanical case, well, the thing has no more velocity with respect to the wall, so there's nothing to damp, right? Okay?
Yes.
Now, these are important questions because it all looks so simple, but there's a lot of little moving parts. Here is the picture, right? So this was his demand line, right? Here you see this. So you see what you do is sometimes economists will say that this is the price margin, right? So this is what's called sometimes you just call this the margin, right? So you make a marginal amount of this at this level of demand, right? So this demand, a price rise of this or a price drop, right, will give me that amount of extra satisfaction. And so I do add V, I increase the price by a little bit, and because of that, I'm going to get some small amount of satisfaction, right? This is how I increase my benefits over that period dt, right? So this is the price margin at this level of demand. So at this level of demand, you know, I jack up the price a little bit. And that area is this. And if I sort this out over the whole integral, then I get this, and I just get this area. All right? That's the graphical way of saying it. Clear?
Yeah.
And you can say, well, how fast am I going if I do this per unit of time, right? And this will be a little vector, and you're going, or you're going, you know, now, and that is the rate at which you're extracting satisfaction or pushing it in, right? And that's the power, is the rate at which you're making this thing acquire kinetic energy or taking it out. Okay?
Mm-hmm.
So what you got to do is you got to line all this up. Now, there really isn't a good name in economics, but you know, look at this. You know, you're changing the price, right? So then I think to myself, why not call this pricing power? Because this is all about the pricing. How much can I jack up the price, right? And still sell this stuff for okay? Right. I'm not sure whether everybody in economics will agree that this is pricing power, right? But what they would do is say pricing power, or sometimes called market power, is the ability to raise the price. Now the wall has definitely got the ability to change the momentum because you can push yourself against the wall, right? I mean, that's what you do. That's action is reaction. So in order to change the momentum of a mass, you have to ricochet against the wall. You have to have they call the recoil has to go against the wall, and the wall will absorb this. If this was some light element, it will shoot away, and you will just fall down. Okay. So the market itself has a lot of market power, right? It can just, and you know that because if you know this diagram, it will just go in a straight line. You know, so you can at any volume, you can sell it at any price. Okay. This is a series market, right? So we put all the inductors in series. If you think about our Thursday discussion, So the surplus with respect to a normal competitive market is slightly different, okay? But the way we define kinetic energy is this way, with respect to an inertial reference frame. And that's why I've done it. So that's again also to Ozai's question, is that all the thing also the surplus? Yes, it is, but you've got to kind of juggle it so that you are sure that it relates in a certain way to the way kinetic energy is defined, you know, with respect to an inertial reference frame. Right? If you just talk about the kinetic energy. Because you really, kinetic energy like surplus is a relative concept, right? So if this thing is moving at a particular speed, you know, now, and this is the other mass, and they have relative to each other no kinetic energy. There's no way to extract anything, right? And now they have a lot. And if you do it with respect to the Earth or the ground, then this thing has a certain amount of this thing, but with respect to each other, they'll have double, all right? So be careful when you make these markers that you're sure that, and that's the same for you, that you're sure that your amount of surplus corresponds in the right way with this kind of rigid idea of what it is, right? I would just specify with respect to what, right? So surplus is always with respect to something. That shouldn't come as a surprise. And if you're all alone in the world, then who are you in trade with? You know, so where's the surplus? You just eat whatever you can eat. And if you have too many apples, then let them rot. Or maybe you're trading with the animals that are also eating the apple. You think those away. You know, it's hard to think everything away. But there's no surplus. It's a little bit harder to imagine in mechanics because we're trained to think of the kinetic energy as if it just exists. No, but really it's relative. Okay? So this is one of these points where I always think like, by the way, this way of defining energy, this is pretty normal in thermal. This is how you would do it. You know? When you have heat engine, is you define the availability as the maximum you can extract. I mean, Ozai is nodding quite vigorously. This is just the way to do it. Huh? So this shouldn't come as a surprise that I think of it this way, all right? In mechanical engineering, also, we just write down this formula, or worse, we would write down this. It's just not numerically correct, but it's not the same thing. You know, that's this area. And we'll come to what the difference is. All right? Any further questions? Then we'll go to the, so we have the R element, the I element. So the R element gives us satisfaction. The I element gives us surplus, and the change of surplus is what I would just call pricing power. But please don't get mad at me when you're confused and says, well, this is not what they call pricing power. Huh? Huh? And now we'll look at the C element. Now the C element, we play exactly the same game. Okay, so again, we're back to our old program. Like, how in heck do we, you know, the program is how in heck do we calculate this thing, right? So we want to get rid of all these T's. We did this in several ways. With the R element, we said, okay, it depends only on the velocity, on the output. With the I element, we have this thing depended on momentum, and this could go in there. And with the C element, we do the last option. Everything depends only on your the stock that you have. All right? Now the C element is also called a holder, so he is a holder of the amount of the sales. So now it becomes really an amount that you have in stock. Okay? And you can control that. The holder can control it. And what the lingo says that if this is then a resource that you can use, so you can sell this later. So sometimes it's called a resource, but it's a resource you can use, you have control over, okay? That you control. And then we say it's an asset. Okay? So assets are resources you control, and resources is an accumulation of an output, okay, from a sales or purchasing. Okay? So the sales and purchasing department goes and buys some stuff, and then they put it in stock, and it's your stock, it's your asset, then you will get the benefits over this, all right? And then in that context, we call it an asset, right? So these things are coming in at a particular rate, and that's what you could call the asset acquisition rate or something like that. And that's precisely the rate at which you're extending that spring, or the rate at which you're charging the capacitor, all right? We went through this. We did all this stuff in future markets, people building up inventory. These inventories are resources, and the one who's controlling the resources, he thinks of it as an asset, right? Now, the assets, if you ask an accountant what the definition of an asset is, and you don't really have to get a real accountant, you can just type it in on the internet, what is an asset? Then what he will say is anything that yields future benefits. Okay. Anything that yields future benefits. All right? So we know what an asset is, and we know what benefits are. That can be measured in the amount of work that you're doing. Right? So an asset is something that yields future benefit. There must be some energy associated with it in the mechanical analog that is equivalent to this. Now, what is the energy associated with the spring? It's called potential energy. All right? What is the energy associated with a capacitor? It's called electrical energy. Right? So the idea of an asset and benefits associated with the holding of these assets, the controlling of these assets is what the analog to that is potential energy, all right? And these things are just called benefits. They're not called surplus. They're just, sometimes you will see that it's called surplus benefits, you know? The way to think about it is not real surplus. It's just there, and it's sort of a potential surplus. When it's sold, so when it's converted to kinetic energy, that's when it becomes surplus, and then you monetize it, then you actually sell it. Now this is just a convenience. It's not actually cash flow that you get, all right? And the way economists will think about it is that the storage induces demand. It's called induced demand or induced surplus. It's surplus that's not real yet, but it has to become real. And the only way to measure it is to look at what the real surplus is. All right? Now, this all lines up really nicely with the way we review potential energy, right? Because how would you do that? Well, what I would do is I would just take this mass, right? That's what I would have done also with the damper. I would put a spring on it, and this mass has a certain velocity. I'll just see how far I get, you know? And then when it doesn't move anymore, I'll just lock it, and then I'll say, all right, at this point, you know, all what was in here that I've already measured is now in here. Why? Because if I let it go, it will just go right back there, and I'll have it again, all right? And I know energy is conserved, right? Okay? So one way to think of this is as the available surplus, of the potential surplus, all right? So potential energy is also called potential energy because it has the potential to be kinetic energy. You know, this is also how historically the concept was developed. So they figured out that they knew what work was, but work cannot be stored in any way, right? It's not a conservative force field, as you might say, all right? So satisfaction itself, you can't really store it. You know, it just gets dissipated. You can store it in entropy, but we'll get to that later, okay? But if you do arbitrary work, you just do some weird thing, you know? You can't say, hey, there's a state variable. But for some special cases there is, like a gravitational field or this or that, is what we could call a conservative field, okay? And what do we do Well, we kind of do the same trick that we do with the mass, but then we flip it around. Okay? You say, all right, these are all functions of time, but now I know that this thing is the change of a state variable. That's the amount you have in stock, right? Before, you have to see V was just some output, but it's not necessarily, and then when I wrote S dot, S is somewhat of an imaginary variable because space itself doesn't know where it is, you know? It really is just, you know, everything you know what S is that it's the integral of V dt, you know? But here, this is a state variable, the asset level. I can just go and measure that, independent of any process, okay? So I plug that in there, but now I know that this is equal to changing the level of my inventory, right? And at the same time, I have the spring law, or the definition of the convenience yield, right? Which says that the amount of convenience is precisely proportional to the amount I have, right? Remember the example of the baker? So now I can express the want in terms of my inventory level, or the asset, my asset as they are booked on the thing, okay? And then I can calculate the integral, right, because I know this, and there you have it, okay? So I get another state variable that doesn't depend on time, right? And I just know what it is at every point in time. I can just take inventory, right? And that's what accountants sometimes do. They don't keep track. They don't keep track of inventory. They don't have good inventory management system. But at a certain point, they got to make up the books. They got to calculate the cost of goods sold, and they say, okay, let's do an inventory check. And they go and have a guy run out and just do an inventory check, right? Nobody integrated queued off. All right, nobody cared how it got there. Nobody cares what's going to happen to it. You just know this is what you have. All right. Now, confusingly, this is what economists also call purchasing power. So if you look it up, you'll say if you have a lot of assets, you have a lot of purchasing power. So you would think an I element is the thing that does the purchasing, and that has the purchasing power, but that's not what they think of. They say this is the power to more potentially in the future start making lots of purchases, and it certainly is, you know, okay? So you can use all that potential energy to jack up the Kennedy, bring up your price, and start trading, you know, all right? But again, this I just, and then you can draw these pictures where you say at this level of the convenience yield, you know, I relieve my inventory by this amount, you know, and I give up a little bit of my potential surplus of benefits, or I accrue some benefits, all right? You get the same picture. So this is the last element, and you can kind of see some satisfying picture emerge here. So we start with this general expression, and we just play some tricks on it. You know, we say, well, we have these two variables, so either we write this as VDP, then I put the F together with the T in one differential. Of course, I need to have some variable P, so it needs to be an element. Or I do, I plug this in there, and that's when I have an inventory, I do that. Or I let these two depend on each other, right? And then I would have F of V times V dt, and I'll still have time, or I'll have V of F times V dt. I can decide what.
That's F.
That's right. Thank you. V of F times F dt. But here you can't decide what to do. So you see here, there is a definite causality. This is the independent variable in the integration, right? You can't just start changing this thing, then you're changing the integrand. I mean, hello, that's just not how integration works, right? So here, the causality is in the change in the price or momentum, which is precisely the force, right? Here you see, you can't just change the convenience yield, you gotta change, you gotta go ahead and buy some stuff or sell some stuff, get rid of some stuff, right? You don't even have to buy and sell it, just get rid of it, Then you can change the convenience yield. You can't just declare this to be less convenient just because you felt like it, you see? So you see, the I and the C of it, they have a definite causality. You can't get around it, all right? That's why writing a half mv squared is wrong, because you can't change this v. You can't change it. How do you change the velocity on a mass? You can't, How do you demand more? You can't just decide to demand more. You got to start bidding it up, right? Changing the price. Some people may think they can decide to demand more on price controls or something, but it never works. Now this damper, right? He can do either or. He can say, all right, you want to transport so many goods? All right, based on that, I'll charge you this much, okay? Got some freight guy or this or transaction guy, So he does it by transaction. How many shares did you buy? How many barrels of oil, right? But you can also have more of a storage guy, and he says, okay, you want to maintain this level of desirability, right? Well, then I'm going to charge you this much, because I need to put an air conditioner in here, because your goods are perishable, and I got to do all this stuff in my storage, right? So they're going to charge you in order not to have losses, right? And if you charge a little less, you're going to have more losses. That's that V kind of creeping out, okay? So you'll have waste, spillage, theft, all kinds of other stuff. So it can go either way. So the cost of carry is either the cost of storage or the cost, what they call the market cost, the transaction cost or market friction, depending on the causality. Because the integration just goes in time. Doesn't matter. All right? So let's quickly put all this together, and then we can successfully terminate this lecture. This is my last slide. I was a little pressed for time here. So I'll do this next week a little bit more carefully, but let me just lay out in the last 5 minutes where this will go to. All right? So one thing you can do now is put it all together. So we'll have, say, a demander, and we have a holder, right? And the surplus can be either in here, or it can be as benefits, potential benefits stored in there, right? Now, if you look at that sum, that's something that we usually call the Hamiltonian. Right? Now, if there's only this going on, then we would say this thing is conserved. Then we prove that, and I will prove that. There's no way of getting more out of this, but just letting this thing oscillate. Okay? And this is like a trader, there's no way to get more out of it. The sum of this is what I would call the economic rent. It's a little bit of a broader concept. It's always hard to see with these guys, but you would see in Shell when they have a really broad concept that we don't know where it comes from, maybe it's in the plans, but they will use the word economic rent. So I would like to think of this as the surplus. This is sort of a potential surplus, but usually it's just called benefits. The benefits of ownership. And then the sum of this will be the economic rent. So next lecture we'll talk a little bit more about that.
So are the benefits or future benefits?
I would just say benefits, because benefits are always in the future, right? This is how they think of it. Like an asset is the possession of the future benefits. So you could say future, but it will be a little, double, yeah, little pedantic, I would say, right? Because it's implied, right?
I don't know what that word means, but I get it.
Well, when you're very pedantic is from pedagogy, very instructor-like, school mastery, right? Normally you have to, belerend, yeah, you know, but it's just, you can do it if a situation has no clarity. Look, all these terms, Jose, it's just, you know, I think it's only that we've lived so long on this concept of kinetic and potential energy, but in the beginning, they didn't know about either energy, they just make it up, you know? Huh? Well, I could call it kinetic surplus or operational surplus, you know, because it's from the operations of buying and selling. So the business usually has, you know, operations, and then they have inventory gain loss, you know, and their profit. You can make all these distinctions, you know. We'll talk a little bit more about it. But, you know, so I don't want you to take it too literally what I say. It's just, I'm trying also to fit terms, you know. And then you can look at how these things change, and the best way to do that is in these bond graphs, and that's where we want to go. So you can clearly see here, you'll have this output, or these sales. In this case, it is a sale because you got this I element. And then you can look at these variables. So here you will see is the power, which is the pricing power. Here a C element, you will see more the purchasing power. And these R element will give you some transaction costs, you know, how they're being subtracted. This is then a source, an effort source. That's more of a general amount of work you can do on it. And you can see that, and we'll talk about this in next lecture, so the preservation of energy, conservation of energy is also the summing of the powers. And this is what we call power conservation. And what economists, I'm going to argue, call the Equi-Marginal Principle, okay? So that you always buy stuff right at the point that the satisfaction derived from that is equal to the satisfaction you lose from having them in there, all right? And you take these services because you have no other choice but to, you know, etc. All right? This is called the Equi-Marginal Principle.
Would it only be when it's equal or when the other one is higher than? I mean, I get that the moment it gets higher, then you would change it. But
it will go in lightning speed too when it's equal, and at that point you will have, and lightning speed doesn't exist. So the theory will say it will always maintain that, okay? All right? Huh? So power is always conserved. The moment that it's not, there's going to be some friction or something that's going to slow it down. So suppose you do this, you have a spray, right, and you just let it go, right? What will it do? It will go to its, you know, original position, right? Now, how fast will it go? Well, this is an ideal spring, it will go with 0 seconds. Is that possible? No, because the speed of light is the maximum, so it's not even theoretically possible, right? So what's really happening here, you know? At the point when it's doing, it still has to do some stuff. It still has to change the price because it has a little bit of mass, right? There's still some friction here, so there's still some transaction cost. And if you add all those up, you'll find the real speed at which it goes to that, right? And in that trajectory, you will always have power conservation, all right? Now, there was a time that they thought power was not conserved, okay? So that mechanical energy could be lost, and that's what you would think, because you take a big bucket and you start stirring it, and then after a while, all your kinetic energy is gone, and can't get it back. And then some very clever guy, Jules, said, well, the only way that's possible, that it doesn't have potential energy, would be there's something else called heat. Okay, and how is that generated? Through friction. How is the way we generate it here? Through an R element. So whatever happens, you're going to have something like that, some entropy generation, right? So those are the two laws that you have in thermo. First of all, this is your first law of thermo, right? Right? So this is all what's going to happen. And the second law says, well, I mean, you can imagine something that goes infinitely fast, but at the minimum, you'll have a small R element that is cooling this whole thing down, all right? So I can imagine something that has no mass, like a photon, right? It is a massless particle, right? But nevertheless, it will, something's going to happen. That's the answer. So what happens is, these are good questions, but what we do in the end, we elevate these things to the level of a principle. That's just the engineering approach. That's what the economists will not do. They will say, well, this will work. And we will say, and this is very important to keep in mind, no, I have these laws, okay? I'm going to adhere to that. If you tell me this is not happening, then I got to look around for something else that's explaining how it can happen within the confines of this theory. All right? Okay, but if you don't do that, then you might as well junk your whole approach. You understand? So this is very important. I find a lot of students saying, well, this is just not what's happening, so I'm just going to make this funky I element with negative mass, and then I'm going to have all this energy disappearing into nowhere, and then I have entropy reducing, and I have this whole list of stuff. And then you may do that, but you're not going to end up anywhere that you can explain at a committee, you know? Huh? You see? Better to take the other route. So, damn the reality, stick to your laws, okay? Right? You're an engineer, you don't really care, right? There's an old joke, I'll end with that, okay? There's a mathematician, an engineer, and a physicist, and they sit together. You guys know this joke? You probably don't, eh? And they're gonna, because you're new to the group. I tell the joke
7 times already.
Yeah, I think.
Yeah, I told the joke already.
I don't remember. So.
Yeah, so let me tell the joke, because it tells you what your attitude should be. And they're going to prove this theorem, and the theorem is all numbers are prime numbers. All right? So, a mathematician goes first. 1 prime, 3 is prime, 5 is prime, 7 is prime, 9 is not prime. Theorem false. Physicist. 1 is prime, 3 is prime, 5 is prime, 7 prime, 9 is not prime, measurement error, 11 prime, 13 prime. Theorem approximately true. All right? So he views it as a measurement. The engineer. 1 is prime, 3 is prime, 5 is prime, 7 primes, 9 prime, 11 prime, 13 prime. Theorem true. Okay? This is how you gotta be. You gotta kind of go to these are the laws. I mean, this is the case. So you know, huh? Okay?
So basically when something
That's exactly how it
so just close your eyes and something is false.
Don't close your eyes, but don't throw up your hand in the air, right? And don't think of it as a measurement error. It's not really a measurement error. It's just that the laws don't describe reality. But that's not the point. The point is to get a model of reality that's good enough to do something better than another person is doing. Okay? That's the point, right? And then somebody can come around and say, well, there's this problem with your, some economists may come and say your design of the smartphone is not quite right because this, and they say, okay, can you do better? No, okay. So it's okay, So it's not about true or false, but whether it works or doesn't work, all right? That's what I want to say. Right? So if this attitude that for the first up to 8 that this theorem is true, up to the number 8 works, then fine. That's more the morale of the story. Huh? So don't even worry about measurement error. Just have a range in which your rules work. This rule works between 0 and 8. All right, 0 and 9. Right? Fine. I can just go with it. That's what I really want to say. Yeah? That's how you have to approach this. But don't throw your rule overboard. You don't have that many. Once you do that, I can't help you anymore. You'll be lost. Huh? You'll become an economist. Or worse, a physicist. Or even worse, a mathematician. Listen, we got to stop the recording, huh? Because we're going outside the purview of the lectures.